Okay, so we are going to continue on in this video with continuous time systems, and we're going to be looking at what's called the impulse response and convolution. And these are basically at the very heart of how we analyze systems in the time domain, and they lead to an understanding of what we're going to be doing as we move forward. The concept is extremely important. The mathematics of it are a little bit involved and can be a bit messy, but a little later on we're going to find ways of circumventing that. So first we're going to concentrate on the impulse response. So we know that we have a mathematical model of a system where we have an input x and an output y of t. We also know that we can decompose any signal, x of t, or in this graph f of t, into a bunch of different scaled and shifted impulses. That's represented by, for instance, x1 at a shift of t1. So imagine that shifted impulse, which has an amplitude of x at t1, is put into our system. Then we will have a response y1, which is just we just represent as the system response to this. But we also know that we can build up a linear superposition of we can rebuild x as a linear superposition. That's effectively what we are representing here, of a bunch of shifted and scaled impulses. And remember, this integral is really just the limit of a sum, so we're basically just summing up a whole bunch of shifted impulses to represent x. And that means that if we know how a single impulse is represented through the system, then when the system is linear and time invariant, we should be able to rebuild y by just summing up those responses as well. So if we think of a single one of these impulses, which is shifted and has some certain amplitude, we should get some output like this. But because we can decompose the input as just scaled and shifted impulses, and if we already know that the system is linear and time invariant, or LTI, then all we really need to know is the system response to a single impulse function. Because if we know that, then we can reconstruct x as a linear superposition of those. Because the system is linear, that means all we need to do to find the response is find the response to that impulse. So let's be a little bit more explicit about that. Okay, so let's take a look at the right-hand side. And so basically, the system operator is operating on the input, and we've just put that inside the brackets here. But we can assume, because the system is linear and time invariant, we can swap the order of integration versus the system operation. Integration is linear, the system is linear, so we can swap their order. And now take a look at what it is operating on. And remember, it's operating on this as a function of t, actually. Okay? But x is just a constant. Remember, that's the amplitude that scales this shifted impulse. So we can pull it outside of the system operation as well because of linearity. And so inside that integral, we can just pull that x of lambda out. And now we concentrate on what this is. Well, this is just a shifted impulse. Okay? So what we're going to do is we are going to define the response of the system to an impulse at time equals 0 as h of t. That's the symbology that's typically used, and that is called the impulse function. We'll talk about that in a second. So if we know that, then that integral for y can simply be represented like that. Okay? So that impulse response is defined in this way, and it is defined as the response of the system to an impulse. The important thing is here, all we need to reconstruct the output for any input is this impulse response. So as soon as we find that, because the system is linear and time invariant, this allows us to reconstruct X as a whole bunch of shifted and amplitude scaled impulses. So if we know the response of the system to a single impulse, then we know, because it's time invariant, that if we shift that, all we have to get is a shifted version of that at the output. And then we could approximate x of t as a bunch of shifted impulses, and each of those shifted impulses has a response, and those could possibly be scaled. Okay? And we just add them together. So we just think of breaking down this signal into individual impulses, finding the responses, and then adding them back up. And that's where linearity comes in. And then as the limit, as that spacing goes to 0, this sum becomes an integral, and this becomes some addition of all of these functions. Okay? Okay, so let's take a look at an example. Hopefully this will help things sink in a little bit. So what we're going to do is we're going to first find the impulse response of this system, which is just an integrator. It takes the input and integrates it. So we're going to find h of t first, and then we're going to find the system response to a unit ramp, given that we already know h of t. Okay, so first we want to find the impulse response. By definition, we just set the input to an impulse. And then h of t is going to be, since it's an integrator, this is the definition of the system. So whatever the input is, in this case it's a delta, the definition of the system is like that. So what's h of t? Well, you may remember that there was a relationship between the impulse function and the unit step, which said that the impulse is the derivative of the unit step, and thus the unit step is the integral of the impulse. And so if you take a look at these two functions here, we can immediately say that the impulse response is just a unit step. Okay? All right. So next we want to find the system response if the input is the unit ramp. So we've already found this. We found that that is the unit step function. Okay? So let's take a look at this definition of the output, and we're going to put in our previous knowledge that we know that the impulse response is a unit step. So it's going to look like that. And then consider what that looks like. Now remember that we're going to be integrating over lambda, so we actually want to graph this as a function of lambda. And note that this is a time reversed signal in terms of lambda, and it's shifted by t. So I should have maybe put this over here, but we know it's a unit step function that's time reversed. And then for any value of t, it's going to be set at a certain value, and then we're integrating lambda up to t. And we'll see why here in a second. So this integral is going to be broken up into two pieces. The first piece goes all the way up to t, where the function is equal to 1. The next part goes from t to infinity, but the function is 0 there. So this portion contributes nothing to the integral. So our representation of the output is just negative infinity to t of the input. Okay, so now, now we're going to find what the response is when our input is defined as a unit ramp. So we want to put this in terms of lambda because we need to stick it under an integral. So remember that the ramp is defined as lambda times a unit step for lambda greater than 0. So it's going to take on a value of lambda, or a slope of lambda, a slope of 1 for lambda greater than 0, and it's 0 if it's less than 0. So just from that previous slide, I'm just going to go back to it for a second. Remember that our integral for y only goes to t now. Okay, and now we're going to put this in here. And note that there are two cases. So if t is less than 0, then we're going to be integrating 0. Okay, because this doesn't turn on until lambda equals 0. So t has to reach 0 before this turns on. Okay, so we're going to get 0 if t is less than 0. And if t is greater than 0, then we're integrating up to 0, but we get nothing. And then from 0 to t, we're integrating this function lambda. And so our result is t squared over 2. Okay, so this output of this system to a unit ramp is 0 if t is less than 0, and it's t squared over 2 if t is greater than 0. And if you think about it, that makes sense. Remember, this is a ramp function which turns on at 0. And so if we integrate that, we have a straight line here. We should get a parabola here. Makes sense. So what is this impulse response, practically speaking? So it's extremely important, and this is why we want to know whether a system is linear or time invariant, because basically this impulse response defines everything we need to know about the system. If we can find the impulse response, we can find the output to any input. What is it, though? Well, you can think of it as the response of any actual system to a little strike. It's like you're hitting something instantaneously and then seeing how it responds. So if you strike a bell, then it rings for a little bit of time. So that's the response of the bell to you hitting it. If you just strike a piano key, don't play it, but just strike it and then let it ring, then that string will vibrate for a little while and die down. So that's the response to the hammer on the end of the key hitting the string. Same thing when you pluck a guitar string. If you just pluck it and don't play it, but just pluck it once and let it go, it vibrates and there's a sound produced for a little bit of time. If we think of it from a circuit perspective, what we're saying is we are imagining that the source of our circuit is just a tiny little voltage spike, and then we see what happens to the system. And it depends at what point you're looking at it. Okay, but that's sort of the practical perspective that we want to have when we think about what is this impulse response. And you can imagine if you go back to, for instance, the piano, maybe that's the easiest for everyone. If I then string together a whole bunch of impulses and a whole different bunch of keys, then I'm putting together a song, or I'm putting together an audio file, and I get this musical response.